Hi everyone, welcome to the class once again. I hope you're all doing good and you're the best of your health. So after learning all the concepts in this chapter of thermodynamics, let's practice question based upon JEE Advanced pattern exercise. JEE Advanced examination, question will be of mixed type. You can get single choice, you can get more than one option correct, you can get integer type, assertion region and even matrix match and even paragraph. So in today's class, we'll be discussing some single choice question based upon JEE Advanced pattern questions on this chapter thermodynamics. I hope you have watched all the classes of thermodynamics and you are ready to practice question with me in this chapter thermodynamics. Let's go ahead with the first question. Question number 1. Starting with same initial conditions, an ideal gas expands from volume V1 to V2 in 3 different ways. The work done by the gas is W1 if the process is purely isothermal, W2 if purely isobaric and W3 if purely adiabatic. So we are given that there are 3 processes the expansion takes place and it is expanding from volume V1 to V2. The work is W1 if the process is purely isothermal, it's W2 if it's purely isobaric and W3 if it's adiabatic. So what we're going to do, we're going to see in which the work done is maximum and how the work done is related in all the 3 scenarios. So first of all, let me show you in the 3 cases, if we draw a PV curve, here I am drawing volume, here I am drawing pressure. If we draw a PV curve, let's say since the gas starts at volume V1, the pressure is P0. Let's say the pressure is P0 and it starts at a volume V1. So in the first case, you see it expands, the work done by the gas is W1 if the process is purely isothermal, W2 is purely isobaric. So W2 if it is purely isobaric, that means there will be no change in pressure. So no change in pressure, so let me show you here, this is the first work done. This is V2. Next thing, in the first case you see it's purely isothermal, in the third case W3 is purely adiabatic. In adiabatic, I have told you the slope will be more compared to isothermal. So what you do, for isothermal you should draw the curve in this way, this will be W1, this is the case for isothermal, and here we have, this is the curve for isobaric, and next for adiabatic process the curve will be somewhat like this. This is the curve for it will be adiabatic, isobaric already we have done, this is adiabatic. So work done during this, the third case is W3, that is what that has been given. Now it's required to compare the work done in all the 3 processes, W2, W1, W3. Clearly from the graph, if you see, maximum work is area under the curve and maximum work done will be max for W2. That is when the process is isobaric, in that case only the work done will be maximum. Next you see the second, it will be W1 for isothermal process and the minimum work will be done in the adiabatic process. So you need not to write the equations for the work done in all the 3 cases. You can just draw a curve, a relative curve, which can give you an idea how will be the work done related in all the 3 cases. It's a very good question, learning question, which you can actually take it and which you can learn how the work is related in all the 3 cases. So W2 is maximum, then we have W1 and then we have W3. W2 is greater than W1 is greater than W3. First one, option number A, that matches with the right answer. Next, B will be incorrect. C, W1 is max, no. D, W1 is max, no. Maximum is W2, that is what we are getting. And this is the how the way that is given to us so that we can get the relation between the 3 work done in the 3 kind of process that we can see. Hope you have got to know how to solve such kind of questions. It's a good question based upon how to evaluate the relation between the work done in all the 3 cases. Let's go to the next question of the class. Question number 2. A monoatomic ideal gas, it's a monoatomic ideal gas initially at temperature T1 is enclosed in a cylinder fitted with a frictionless piston. The gas is allowed to expand adiabatically. Adiabatic, that means there is no heat change, to a temperature T2 by releasing the piston suddenly. It's an adiabatic process. If the L1 and L2 are the lengths of the gas column before and after expansion respectively, then T1 by T2 is given by. T1 by T2 we need to compare, and volume is what that has been given to us. So first of all, For adiabatic process, we know that you can write for adiabatic process Tv power gamma minus 1 is equal to constant. This is what we can write. Tv power gamma minus 1 is equal to constant. So we can write that temperature is inversely proportional to 1 upon V power gamma minus 1. This is what we can write. Now it says that an ideal monatomic gas initially temperature T1. Let's say the initial temperature is T1, that is provided, and the initial volume is V1. So we can write that T1 will be proportional to 1 upon V1 power gamma minus 1 and T2 will be inversely proportional to 1 upon V2 power gamma minus 1. This is what we can write. Now if we take the ratios T1 by T2, because here it's required the value of T1 by T2. So T1 by T2 ratio will come out to be, that will be equal to, what you do, you take this V1 will move, V1 will be in the denominator, so bring V1 here and V2 will go in the numerator and power gamma minus 1. This is what we know. Now it's given that it's a monatomic gas. For monatomic gas, the value of gamma is 5 by 3, that is what you can use, 5 by 3. So T1 by T2 will come out to be is equal to, now for volume V2 by V1, you can write that as A into length. So A into L2 divide by A into L1 power 5 by 3 minus 1, you get that's 2 by 3. So it will be L2 by L1 divided by 5 by 3 minus 1, you will get 2 by 3. This is the answer for the ratio of temperature in the two cases, L2 by L1 power 2 by 3. Let's go ahead and check T1 by T2, L1 by L2, no, it's not L1 by L2, it's not L1 by L2 anything, L1 by L2 power 2 by 3, no. C L2 by L1, no, this is not we are getting, and D L2 by L1 power 2 by 3, yes, this is the answer that we are getting. A very good question to relate, because here we know that adiabatic process we need to use this equation. You will be confused that adiabatic constant, to use it, adiabatic process we don't know that PV power gamma equals to constant. From there PV power gamma equals to constant, you can actually derive this result, and then you can proceed accordingly to reach to the final calculation of T1 by T2. Hope that you are getting, with each of the question we practice, you are enhancing your skills and you are getting to know how to solve such questions. Let's go to the next question of the class, question number 3. In a given process of an ideal gas, dW equals to 0, that is work done is 0, and dQ is less than 0, then for the gas the temperature will decrease, the volume will increase, the pressure will remain constant, the temperature will increase. First of all, it's given that let's use the concept of first law of thermodynamics. The first law of thermodynamics says that dQ is equal to du plus dW. Now dW is 0. Given that dQ is less than 0, that means heat will not be supplied, rather it will be extracted from the gas. dQ is less than 0 provided. So if dQ is less than 0, therefore du will be less than 0. We all know this. So internal energy is going to decrease. Internal energy is going to decrease, that is decreasing with time, it decreases. Internal energy decreases. So if it decreases, what does that mean? What does it imply? It means that since internal energy is directly proportional to temperature, U equals to NCVT, that is what we know. U is equal to, or you can write U is equal to NF by 2 RT. F is the degree of freedom. This is what we know. So U is directly proportional to temperature. Internal energy decreases, that means temperature has to decrease. It has got a direct connotation with temperature, it has to decrease. So we all can comment that temperature decreases. So it's a single choice question, the temperature will decrease. Yes, option number A is the correct response. B, the volume will increase. No, we cannot comment on, because in the gas dQ is less than 0, there is no work done. The volume is going to remain constant. The pressure will remain constant, that's not required. We are holding the piston at the same position. Pressure will not remain constant. The temperature will increase. We all seeing that temperature decreases. So even this is incorrect. Rest three options we have logically come to the conclusion B, C, D are incorrect, and A will be the only correct option here. Let's switch to the next question and hope that with each question you are learning the concepts in a better way. Next question of the class, question number 4. An ideal gas enclosed in a vertical cylindrical container supports a freely moving piston. It's a freely moving piston of mass m. The piston and the cylinder have equal cross-sectional area. When the piston is in equilibrium, the volume of the gas is V0 and its pressure is P0. So, volume and pressure is given. The piston is slightly displaced from the equilibrium position and released. It's displaced and released. Assuming that the system is completely isolated from its surrounding, the piston executes a simple harmonic motion with frequency A, B, C, D. You can check the options. It's given in terms of area and then P0, V0, M. It's also given in terms of gamma also. You can see it's gamma, your A into gamma. Think that it's gamma is multiplied. It's not in the suffix. Next thing, and here also gamma is in suffix. So, how to find out? First of all, let me tell you it's a case of adiabatic process, and you can see, because see what is happening here. First of all, there is a piston. There is a piston, there is a cylinder. Let us say this is the case. This is the piston. The pressure is P0, the volume is V0, the pressure is P0 and the volume is V0. We all know that, dP by dV is equal to minus gamma P0 by V0. This is what we know. Next thing you try to understand, at equilibrium what we can write. At equilibrium we can write that P0 into A, pressure into area, is equal to M into G. This is what we know. In equilibrium this will be holding. Next thing, after this, how to proceed? We all know that force is equal to minus k into x. If we from any means we come to know that what will be the value of force when the piston is displaced. See, if the piston is displaced, the external force, the extra force will come out to be dP into V. dP into V. So, F will come out to be dP into dV. That is what you are going to get. That will be the value. Now, how to find out this dP into V? First of all, dP will come out to be, you can write F as dP, that is minus gamma P0 V0 into dV minus gamma P0 V0 into dV, and here you have V. That is what you can actually express. So, finally, you will be getting this as minus gamma P0 by V0. dV will come out to be A into dx, and V will be equal to A into length. That is what you can actually comment, because finally you will be getting this as A into length L, and here you will be getting dV as A into dx. Or let us keep it as, this is not required, let us keep it as V0. V0, that is actually given. So, let us keep it as V. So, what do you take note till here? Let me start at the other end, take note till here. Okay, now you see one thing, I have written here F is equal to dP into V. Most of you would have noticed that F is not dP into V, F is equal to dP into A. This is what you should know. Now, dP into A, here you can express this as we have used this, dP into A, and dP we have written as minus gamma P0 by V0 into dV, and here you have to use this as A. So, finally, you have to use the just some values you need to change, minus gamma P0 by V0. A, keep it as it is, dV will be A into dx. The small displacement that you have given, that you have taken as dx, that is what we are taking. So, let us open this, you will be getting F is equal to minus gamma P0 by V0 into A square dx. This is what we are obtaining. We all know that in the case of simple harmonic motion, how force is related, and that is equal to F is equal to minus kx, or in this case let me take this as dx. So, finally, the constant k, you will be getting that as gamma P0 by V0 into A square. This is what you are going to get, gamma P0 by V0 into A square. This will be the constant. Next, you see we got this. What's the frequency? It's required that simple harmonic with frequency. It oscillates in time in the kind of simple harmonic motion with frequency. Frequency we need to evaluate. The frequency of any simple harmonic motion is given as 1 upon 2 pi k by m. This is what that has been given. Substitute the value of k that we have obtained. Let me rub this part. The k that we have obtained, if we substitute it as gamma p naught a square by v naught, so f comes out to be 1 upon 2 pi under root gamma p naught a square by v naught. So mv naught, let me substitute in this way. 1 upon 2 pi gamma p naught a square upon mv naught, this is the thing that we are obtaining. Let's check with the given option. We are having option number A, 1 by 2 pi a into gamma p naught by v naught m. There is no under root, so this will be incorrect. Then again 1 upon 2 pi v naught is in the numerator, incorrect. And here 1 upon 2 pi under root a square gamma p naught by mv naught. And here we have 1 upon 2 pi gamma p naught a square by mv naught. This is the option that is matching. So the correct answer will be option number C. And here just reverse is given, so you can say that this is incorrect. So correct answer will be this, 1 upon 2 pi under root a square gamma p naught by mv naught. The examiner tries to check that whether you have solved questions, whether you have learned in detail, you have solved questions, then only you can proceed with such kind of question. Because you don't know, if you don't know how to use the concept of dp by dv equals to minus gamma p naught by v naught, and in the case of derivation also, while deriving the adiabatic relation, I have discussed all these things. Hope that you have understood how to solve such kind of questions. It's a good question, and this question has been asked in the previous examination, so you must be knowing that what kind of question the examiner can ask from you. Question number 5. 2 moles of ideal helium gas are in a rubber balloon at 30 degrees Celsius. So initial temperature given 30 degrees Celsius and 2 moles of ideal helium gas. So number of moles is 2 and initial temperature is given as 30 degrees Celsius. That is equal to 273 plus 30, that is will be 303 Kelvin. Let's see which one we need to use. Next thing you say, the balloon is fully expandable and can be assumed to require no energy in its expansion. The temperature of the gas in the balloon is slowly changed to 35 degrees Celsius. The amount of heat required in raising the temperature is nearly. Take R equals to this much, that is the standard value of R, A62, B104, C124, D208. It is freely expandable. That means pressure will remain constant. That means it's a gas that is actually expanding. We can use the amount of heat energy supplied, delta Q can be taken as NCP delta T. This is what we can use in this case. It's a helium gas, that is what we are discussing here. It's a helium gas. So we need to know the value of Cp for helium gas. We need to know that what is the value of delta T. So what I'm going to do, I'm going to write the value of N, that is 2. We know that delta T, since it is taken from 235 from 30 degrees Celsius, so it will come out to be 5 degrees Celsius. This is what we need to put here, and all the things are given here. You can find only the value of delta Q, the amount of heat required in raising temperature. So we have done the maximum part. So let me write at the other end of the board. So just take note till here. Let me write at the other end. So after knowing all the values, we can easily substitute the given variables value. So let me substitute here. We'll be having delta Q is equal to N, that is 2. Cp you can take as 5 by 2R for helium, and delta T as 5. In Kelvins also it will remain the same. So this value will come out to be 2 will be cancelled out. So it will come out to be 5 into 5, 25, and the value of R is 8.31. That is what that has been given to us. Now if you calculate this, you will be getting around 107.75 joules. That is what you can do. This will come out to be around 107.75 joules. That will be around 207. I have did 107. That will be around 207. And after this, you see that this is nearly equal to 208 joules. You can check the calculation. It will be 208 joules. So the correct answer will be the amount of heat energy required will be 208 joules. So now you would have understood in where you have to use the formula NCP delta T to calculate the heat energy supplied, that is 208 joule. Rest all the options are incorrect. Hope that you have understood how to solve such kind of question. It's a good question, and this let us understand that the method to use NCP delta T for the heat energy supplied.